Hello everybody. Welcome to our stats video for the week here. We're going to have a few coming up here. It says Unit 5. We're still in Unit 4, but in the past I've broken into separate units. But with our time crunch this year with the COVID, we're going to join it back as Unit 4. So anyways, we're introducing random variables. Random variables, okay, it's just any event that has several possible outcomes. So it's not really a good definition of much. Okay, but can assume, it says numerical value, any of several numerical values as a result of a random event X. Okay? A discrete random variable, which is what we're working with first, okay, can be one of a finite number of distinct outcomes. So I can only have certain results. If I play a card game, I can only get this, or that result. I could win, let's say I'm playing a game, and I can either lose and win nothing, or I could win $5, or I could win 10. The outcome of the game are only those things. I can't get like $2.50. That's not a possibility, okay? In a continuous random variable, it's usually dealing with maybe like time, where how long does it take you to fix a car? Or to do a tune-up or something. Well, it could take from here to there, but anywhere in there could be an answer, okay? So discrete means a distinct numeric value. There are only a few of them, usually 3, something like that, okay, that the random variable could take on. Again, the random variable X could stand for winnings at a card game, and it could take on the values of 0, 5, or 10 maybe, okay? All right, continue again, can take on any numerical value within a range of events. The range may be finite or infinite. And I hope we can see this. The probability model associates, and bring that up. Probability model associates a probability P with a particular value of a discrete random variable. Okay, so this might be like this X. By the way, this took me a while. Like I've told you before that I had to learn this myself, kind of on my own. In the beginning, I didn't understand what this was. Okay, this stands for the event itself. This would be like winnings. Okay, in the example I talked about, and this could be a particular value of it. So the probability of X, you're winning, equaling say $5. That's what would go there. Would have whatever calculation it takes to do that. That's what this stands for here. So X is your event, like winnings in our case. And it would equal whatever number we're talking about there, one of the possible values. Okay? All right, expected value. They're going to ask you to find, typically, the expected value and the standard deviation of a certain random variable or a certain outcome. Okay, we'll be seeing that in a minute here. All right, but for now, it's the theoretical long-run average, okay? Note it is the mean, but it's usually represented as the expected value of X, okay? The way we find that for a discrete random variable is we time each thing, it'd be like $5 or 0 times the probability of that happening, okay? And this is the sum of that, we total that up, okay? And that will calculate the expected value. In other words, if I were to play a card game many, many times, what's the expected outcome for me? Well, I would win $0 or 5 or 10, maybe like we said in my example I gave you. But in the long run, I might end up earning like $7.50 per average per game. That's the long run average, okay? Again, each item, each outcome that's possible, multiply the probability of it happening, and I'm going to add those all together. All right. Okay, the variance. The variance is very important because we're going to need to be working with variances a lot in this unit here. That's the standard deviation squared. In other words, before you square root it, okay, the variance of X is equal to each one minus the mean, which you found here, that's E of X could go there, squared multiplied by its probability. Okay, and then ultimately, we're usually after the standard deviation, we would square root that value, the variance, okay, and get our standard deviation. All right, this is really big here, guys, okay? So let's say the expected value over the long term, if I played it again and again, this card game I've been talking about, that I was expected to win $7.50, okay? Well, if I play 2 games, watch, that's 2 separate events. It's just not 2 times it. For now, it might seem silly to you because the math is the same here. but I would have game 1 and game 2, okay, and the expected value of game 1 would be 750 plus the expected value of game 2 would be 750. If I played twice, I would expect to win around $15, okay, which totally makes sense. Your expected values always are things that I almost don't need to teach you at all, okay, but our variances are different here now. Okay, the variance of 2 games are 2 separate events, so each time I play, there's a range of things that could happen, and I play again. Now when I double those, I could get like a really low result or really high result. I could win $10 in each game and get up to 20. Okay, so it's more than the original possible variation or spread of the data. I have more things that can happen. So the variation of 2 events would be the variation of the first plus the variation of the second. Okay, and then I'd want the standard deviation, I would square root that. Okay, I need you to note that you cannot add the standard deviation together, okay, to get the new standard deviation. You'll get the wrong answer. Okay, I must add the variances, and then when I get my new variance for multiple events here, then I'll square root that, and that'll be the correct standard deviation. Okay, and this is the big one here. If I have two events that I'm subtracting, finding the difference between those 2 events, okay, then I would subtract the 2 events, the expected value as you would expect, okay, but my variance, okay, if I add 2 events together, I'm going to add them, but if I subtract 2 events, there's still lots of variation that could happen. It increases the variation in the 2 events, okay, and I will still add it. So even if there's a minus here, which we'll see later again, I need you to note that variances only add always. All right? Thank you.